So, we were looking at ideal gases and pure substances before that, and we also looked at examples where we calculated the specific gas constant R, which is the ratio of the universal gas constant to the molecular weight, Cp, which is the specific heat at constant pressure, and Cv, which is the specific heat at constant volume for an ideal gas. In this case, it was nitrogen. What we see is that Cp and Cv may or may not be constants. So, the number of degrees of freedom which a gas has may change with temperature, because the vibrational modes get excited at higher temperatures, and the fraction of molecules which are in these other modes of excitation will increase as the temperature increases. As a result of this, both Cp, Cv and gamma vary as the temperature changes. So, we can look at some values of these for typical gases. So, for example, if you look at gamma, the ratio of specific heats, this first two columns here are for dry air. We see that at about 0 degree centigrade, the value of gamma for air is about 1.4. At 20 degrees, it is actually 1.4. And as we go to higher temperatures, the value of gamma reduces. The value of Cp and Cv individually increase, but the ratio of Cp to Cv, which is gamma, reduces as we go to higher temperatures. So, we find that by the time we reach about 1000 degrees centigrade, we are at a Cp to Cv ratio of about 1.36 instead of 1.4, and about 2000 degrees centigrade, the ratio, which is gamma, is only about 1. Similarly, with a triatomic gas, which is CO2, if there were only the translational and rotational modes, we would expect gamma to be about 4/3, which is about 1.3. We see that at 0 degree centigrade, it is actually 1.3, and as we go to higher temperatures, the value of gamma comes down. It goes to about 1.2 at 100 degrees centigrade, about 1.23 at 400 degrees centigrade, and by the time we reach about 1000 degrees, it is only about 1.1. And a similar trend we see for argon, where it comes down from about 1.76 at minus 180 to about 1.67 at 20 degrees centigrade. So, at very low temperatures, the gases do not behave as if they are ideal, because there are still interactions between the molecules. At very high temperatures, we see that the Cp and Cv increase, because a lot of the energy goes into other forms of for example, in vibrational modes, and gamma itself reduces. So, if we had an ideal gas whose specific heats are constant, we would call that as a perfect gas. So, a perfect gas is one where Cp or Cv are both constant. So, they do not change with temperature, and if these two are constant, then gamma, which is the ratio of Cp to Cv, also must be a constant. So, if I was to plot either Cp or Cv versus temperature, what I would see is, for example, I have 100 degrees centigrade here, I go to like say 1000 degrees centigrade here. Cv would be constant, so it is a straight line parallel to the t axis. Cp would also be constant, so it is another straight line parallel to the t axis, and the difference between these two would of course be the specific gas constant R, where Cp and Cv are the specific heats in units of say joule per kg Kelvin, and R would also have the same units, and the difference between Cp and Cv would be R. So, all these would be constant if we had a perfect gas. These are also often called as calorically perfect gases, and it essentially means that Cp and Cv are constant. So, we know that the internal energy for an ideal gas is given as Cv into T, and the enthalpy is given as Cp into T. So, if we have Cv and Cp as constants, so this takes the form of some y equal to m into x if you plot u versus t, which is the equation of a straight line which passes through the origin. So, we can see that, for example, this is either u or h. So, u versus t is a straight line, and the equation is u Cv into T. Enthalpy versus temperature is also a straight line, and this would be the case if we had Cv and Cp as constants, and we call these as calorically perfect gases. So, if we look at gases where Cp and Cv are not constant, which is what we saw would usually happen, those are the gases which we call as semi-perfect gases, provided Cp and Cv are functions of temperature alone. So, if we have Cp changing with temperature and Cv changing with temperature, but not changing with pressure or specific volume or something like that, we would call it as semi-perfect gases and or generally ideal gases. So, we would call these as perfect gases and these as semi-perfect gases or simply as ideal gases, because they follow the Charles law and the Boyle's law and the Avogadro's law and so on, but they do not have Cp and Cv as constant. And if we were to plot Cp and Cv, what we would see is that Cp and Cv increase with temperature, and correspondingly we see that if you plot enthalpy or internal energy as functions of temperature, they are no longer straight lines, because it is now some U is now some Cv, which is itself a function of temperature into temperature, and we have enthalpy which is Cp, which is a function of temperature itself into temperature. So, we see that since this is not a constant, this is no longer a straight line, but it tends to have some shape of this form. So, if they are constant, we call them as perfect gases. If they are not constant, they are just regular ideal gases or semi-perfect gases. So, this is the variation of either Cp/Cv or internal energy and enthalpy with temperature for gases.